today we're going to get into the combined gas law. And when I say combined, you're talking about pressure, temperature, and volume, okay? Pressure, temperature, and volume. So let me put the formula on the screen for you guys so you can see that, okay? And I appreciate all of you guys that were tapping the screen because, you know, that's important because it lets everyone know in TikTok that, hey, Professor TK the Chemist is giving away free tutoring, and everyone needs to know about that because a lot of you all are having trouble in your chemistry classes and you need extra help, okay? And the only way you're going to be able to get that help is by going to your professors, to your teachers, and if that doesn't help, you can always come over here on this platform with me. All right, so let's go ahead and get into the combined gas law. The combined gas law deals with, of course, pressure, volume, and temperature. So here is your formula right here. P1 times V1 over T1, which equals to P2 times V2 over T2, okay? That is your combined gas law. But the thing is, I can actually rewrite this to where everything is linear. So that means you're going to cross multiply, okay? So what I would end up getting can look something like this, where I have P1 times V1 times T2, which all of that is equal to P2 times V2 times T1, okay? So that's like in some books, you will see an example like this in terms of the formula. So they could be actually written in two different ways, okay, where you are cross multiplying, okay? Now, here's the thing though. If I want to get, let's say the formula for P1, all I have to do is multiply these three sides here, these three variables here, and then divide by these two, okay, right there, okay, while you're looking for P1, okay? But I will show you guys that as we get to problems in this particular nature. So for the first problem that I have, okay, whenever you're dealing with the combined gas law, what you need to realize is that your moles are held constant, and that's going to actually play a role in what we talk about later today in terms of Avogadro's gas law, okay, because that deals with moles. And remember, moles is something that we've dealt with before. So right here, okay, I'm going to go ahead and pull up this first problem for you all so we can actually get into this one. And let me find it. Hold on, guys. Okay. So when you are doing the combined gas law, you're going to be given pressure, volume, and temperature. Pressure, volume, and temperature. Okay. I thought I had pulled the problems up. Apparently I did not. Hold on, guys. Let me find it. Let me find it. Nope. Okay, hold on. So what I'm gonna do, okay. All right, y'all. So I'm going to kind of switch the gear a little bit. I thought I had it pulled up, but I didn't. So I'm just going to do this then, okay? So for those of you guys that are here with me, you guys can see this one, right? And it says, and I'm just going to kind of give you the information here, but I'd rather have it out. So I'm just going to type it so you all can see it, okay? It says a sample of hydrogen gas has a volume of 65.0 milliliters at a pressure of 0.992 atm and a temperature of 16 degrees Celsius. What volume, and I'm going to increase this so you all can see this. What volume will the hydrogen occupy at 0.984 atm and 25 degrees Celsius? Okay, so we got several things going on within this problem, okay? And what I'm going to do is show you guys how to solve this problem without any hesitations, okay? So right here, again, here's your problem. I'm going to expand this so you guys can see it, okay? So you all can pick out the notes and things that we need in order to solve this problem, okay? So here it is again. A sample of hydrogen gas has a volume of 65 degrees, 65.0 milliliters, sorry, at a temperature of at a pressure of 0.992 atm and a temperature of 16 degrees Celsius. What volume will the hydrogen occupy at 0.984 atms and 25 degrees Celsius? Okay, so here is what you've got in this problem. You have to find out what your P1 value is, your V1 and your T1, P2, V2, T1, okay? So when we do a problem of this nature, I always tell students to write out what you're given so you'll know how to solve the problem. So right here, the first thing they gave you was the V1, okay? They gave you P1 right here, and I'm highlighting everything in purple. The T1 is 16 degrees Celsius. Here is the thing though, your temperature must be in Kelvin. In order to do this problem, your temperature must be in Kelvin. Now, the next thing you also have in this problem, okay, it says what volume, so that's your V2, I'm putting that in yellow, will the hydrogen occupy at 0.984 atms, that's your P2, and your T2 is 25 degrees Celsius. So everything that I highlighted in purple is the first concentration values, or the first values rather, or the initial values. And then the things that I highlighted in yellow are your secondary or final values, okay? So I like to write everything out so that everyone can see how these things work, so that you will also know that you're able to predict what the final answer will also become as well, okay? So your P1 was 0.992 atm. The P2 is 0.984 atms. So I know that my pressure has dropped. My first volume reading was 65.0 milliliters. But remember, in yellow, they ask you for what is the volume. So in other words, the final volume reading, okay? So that's where my question mark is going to go. My first temperature reading was 16 degrees Celsius, but remember, we must convert that to Kelvin by adding 273 to that number, and we end up with 289 Kelvin. The second temperature reading was 25 degrees Celsius. Again, we're going to add 273 to that, and we get 298 Kelvin, okay? So far, so good. This is what you have for your values. Now, what you're going to do is figure out what the formula should be for V2. Now, since I have everything here on the left-hand side right here of this formula, I'm going to go ahead and put that down. P1 times V1 times T2. Okay, that's going to be my formula right there. P1 times V1 times T2 divided by, okay, since we're looking for V2, according to our formula here, we're going to move, what I'm going to highlight in yellow, we're going to move P2 and T1 underneath the other values that I already written down. So P2 and T1 are going to be written down underneath my formula, okay? P2 and T1. So that is the formula that we're going to use right here to solve this problem, okay, to solve this problem. Now, notice that your temperature increased. Now, if we remember Charles's law states that if the temperature increases, the volume will increase. If the temperature drops, the volume will also drop. So the thing is, though, you're using a combined gas law. So will that hold true here? We're going to find out. We're going to find out. If we are making an assumption that our temperature increase, therefore our volume will increase, well, let's determine what happens here based on our pressure. Our pressure decreased, therefore our volume will increase according to Boyle's law. And that's why they call this the combined gas law. So in other words, we're able to predict the answer based on using both laws at the same time. Okay, at the same time. So in this particular case, I can guesstimate that our volume will also increase, okay? It will also increase. So the number or the answer that I'm going to be searching for, if I were doing this as a multiple choice answer, I would need to look for a number greater than 65. So the predicted answer that we're looking for must be greater than 65 milliliters, 65.0 milliliters, okay? The number should be greater than 65.0 milliliters. So now let's go ahead and try this one out right here, and let's plug it in to what we've got, okay? So we're going to plug this in right here and to our formula, okay? So right here, let me go ahead and scoot this down so we can have some space. And thank you guys so much for those Easter eggs or Easter bunnies or whatever is popping up on the screen. That again, that's letting the analytics know that we are doing something good over here when you guys hit that screen. All right, so let's go ahead and rewrite the formula in the correct manner so that we're able to plug these numbers in. And we're going to also cancel out our like terms, okay? We're going to cancel out our like terms. So our P1 in this case is 0.992 ATMs, 0.992 ATM times V1, which was a 65.0 milliliters, and my T2 is 298 Kelvin, okay? Divide that by P2. So the second pressure reading was 0.984, 0.984 times my T1, which was 289 Kelvin. Okay, what we need to do, of course, is cancel out our like terms. We don't need the ATMs anymore. We don't need our Kelvins, but guess what's left over? The milliliters. So that's what we're solving for. And remember, we're predicting that our answer will be greater than 65.0 milliliters. So what I'm going to do is plug this number in, 0.992 times 65 times 298. All of that divided by 0.984 and 289. And I get 67.56, but because we need 3 significant digits, our answer will become 67.6 milliliters. Isn't that greater than 65? I mean, it's a little bit greater, but the answer is more than 65 of what we predicted that the answer will become. So in this particular case right here, this is our final answer, 67.6 milliliters. Okay. Any questions from anybody about this problem? Okay. So now, when you get to a problem like this, because this is the combined gas law, okay, all you're doing, and let me show you all again, mathematically speaking, how you can easily predict the answers, okay? How you can easily predict the answer. I'm going to show you all something real cool, okay? And I'm a visual person. So, and because I'm a visual person, I got to draw it out so y'all can see it. Okay. Boyle's law, if you recall again, if the pressure goes up, the volume will go down. The temperature remains constant. If the pressure goes down, the volume will go up. The temperature still remains constant. Something else you can remember as a visual perspective, if I told you that the pressure increased, okay, the pressure doubled, the volume is going to be cut in half. If I told you that the volume, let's say that the volume tripled, okay, then you know that your pressure is going to drop by a third. So in other words, they're called being inversely proportional to one another, inversely proportional, okay? That means they're opposites, okay? Think of it that way, they're opposites. If one goes up, the other one's going to go down. So if I increase the pressure, okay, of one thing, then the volume is going to drop, and vice versa. However, if we're dealing with Charles' law, okay, Charles' law states, okay, again, as a summary, so you all can see this and how I'm able to use that even with the combined gas law. Charles' law deals with temperature and volume where the pressure remains constant, okay? The pressure remains constant. So in other words, the pressure is not going to change. If my temperature goes up, my volume will also go up. If my temperature goes down, my volume also will go down. The pressure will still remain constant. So that means if my temperature doubled, guess what? My volume is also going to double. If my temperature, dropped by a fourth, guess what? My volume is also going to drop by a fourth. So in other words, they're going to do the same thing. And that's why when we go back up here to our combined gas law, we're able to predict what the answer will be just by knowing that, for instance, if we looked at our pressure again, our pressure decreased, so our volume should increase according to Boyle's law. But if I'm looking at the temperature and the volume, I know that my temperature increased, therefore my volume will increase. So you can actually use two gas laws into one problem and still come out with your answers, okay? That's how simple this is. Now, I'm going to move you guys on now to the other law, okay, that deals with the Avogadro's law, Avogadro's gas law, okay? So when we talk about Avogadro's gas law, it deals with moles, okay? They deal with moles. So let me show you all what I mean by that, okay? When it comes to Avogadro's gas law, what do you mean, Con? You said your college dean forced you to meet with them for what? It depends also if you're on, are you on academic probation? Are you getting a scholarship? For what? Then you need to email them back and ask them what they need to meet with you for. It might be about your program. So take a look at this next problem, okay? This one deals with Avogadro's gas law, okay? You're dealing with moles and volume. So if you noticed here, you've got several things going on, okay? Just go to them. What's the worst that can happen if you meet with them, okay? You're just going to find out what they need you to know, okay? So in this particular problem right here, you've got V1 and you've got N1. Again, your N stands for moles, okay? V2 and N2. So let me read this problem so you all can see what you have to do for this one. A weather balloon with a volume of 44 liters is filled with 2.0 moles of helium. To what volume will the balloon expand if 3.0 moles of helium are added? To a given total of 5 moles of helium, the pressure and temperature do not change. So now they're telling you several things in this problem, but you have to make sure that you don't get sidetracked with what they're giving you in the problem. A lot of times you can be given certain numbers and you might get sidetracked thinking that they're telling you certain things that you don't need or that you do need, okay? So in this particular problem here, they're saying that you have 44 liters, okay? So that's the initial amount. They're wanting you to find the final volume amount. They also initially gave you 2.0 moles of helium. They said that they added 3 moles of helium to give a total of 5 moles. You cannot get tricked when you see 3 different mole numbers. The final number, the 5 moles, is the final assessment that you would go by, not the 3. The formula for this, guys, is V1 times N2, which equals V2 times N1. Now, how do you establish the answer for this? Here's the thing. If the volume increases, the moles will decrease. If the volume decreases, the moles will increase. So this is similar to Avogadro, this is similar to Boyle's law, okay? Where they're inversely proportional to one another, okay? But let me double check y'all with that one to make sure that we're clear on what we're saying right here, okay? So, not double. I'm sorry, not decrease. They're the same as Charles' law. Sorry about that, guys. If the volume increase, the moles increase. If the volume drops, the moles also drop. So this is similar to Charles' law, okay? Similar to Charles' law. So just so you guys can figure this out to guesstimate what the answer should be, take a look. Notice how your moles was 2.0, right? And then it went up to 5. So just by looking at this alone, this tells me that my moles doubled and a half. It went up by 2.5. So guess what your volume is going to do? It's going to also go up by 2.5. Now, if you want to make sure that that is so, and you have to prove this on your paper or on your test, we need to do the math. And doing the math means we're going to plug these numbers in to our problem, okay? So here we go. I know that the formula says I'm looking for V2. So since I'm looking for V2, that means I'm going to say V1 times N2 over N1. That is my formula to solve for V2, okay? So my V1 that they gave me in the problem was 44 liters. My N2 was 2.0 moles. And my N2 was 5.0 moles. Sorry, guys, 5.0 moles. And my N1 is 2.0 moles. You're going to cancel out your moles because you don't need them. And now we just need to plug this into our calculator, okay? So that's 44 times 5 divided by 2.0, and we get 110 as our volume, okay? As our final volume, 110 liters, okay? No, Happy, I do not teach computational chemistry. So that is your answer right there. Now, how do we know that? Well, look, we were able to make an assessment because remember, Avogadro's gas law is similar to Charles in terms of saying that if one of the variables increases, the other variable is going to also increase, okay? If one of the variables decrease, the other one will also decrease. So in this particular case right here, when we were looking for our volume, okay, we knew that it would double in a half based on the fact that our moles doubled in a half, okay? So that's how simple these problems can be. They're not hard at all. You just have to remember to know what you're given and what's required, okay? Look at what's given and what's required. Now, I'm going to do this next problem right here. But let me tell you, you've got to read the problem because there are some tricky things in there, okay? So let me go ahead and cut this out or crop it so that you're only focused on certain parts of this problem, okay? So we're going to look at problem 14.5. We're going to actually look at 14.5. Let's do B, okay? 14.5B. All right, so right here, in your problem, and let me put the formula back up here again so you all would know it's V1 times N2 equals V2 times N1, okay? That's the foundation of the formula that we're going to be using, and we can flip and reverse this formula depending on what we're looking for, okay? So 14.5, we're doing letter B. For the sake of time, we're going to do letter B, okay? A sample containing 1.50 moles of neon gas has a volume of 8.0 liters. What new volume of the gas in liters will occur when the following changes happen? So right here, we're given the 3.5, a sample of 3.5 moles of neon is added to the 1.5 moles of neon gas in the container. So what you have to do is read the problem and not overthink what they're telling you in this problem, okay? So let's get this down here for my visual learners and write out what they told us. Okay. It says a sample containing 1.50 moles of neon has a volume of 8.0 liters. What is the new volume when a sample of 3.5 moles of neon is added to the 1.5 moles of neon gas? So in other words, you're adding the 3.5 plus the 1.5 to give us 5.0 moles, okay? That is your final mole number. You have to learn to read between the lines of what they're giving you and not overthink this, okay? They're just telling you that they added 3.5 additional moles of gas or moles, okay, of gas to this container. So that's how you end up with 5.0 moles. Now, what did you notice here? Our moles did what? They increased. Since our moles increased, you know your volume is going to do what? It's going to also increase. So whatever answer you're looking for must be greater than 8.0 liters. So what we're going to do, because we're looking for B2, you're going to go back to your formula again, okay, right here. And all you're going to do is say V1 times N2, okay? V1 times N2 divided by N1. Okay? So now you've got 8.0 liters times 5.0 moles divided by 1.50 moles. Cross out your moles because you don't need those anymore. And let's plug this into our calculator to see if we got it right. You've got 8.0 times 5, which is 40. Divide that by 1.5, and you get 26.7. But since we only need 2 significant digits, our answer is 27. So our V2 is 27 liters, okay? 27 liters. And as you can see here, to go to 27 means that our volume did increase. Now, take a look at letter C, because letter C, they're now telling you grams, okay? They're giving you grams. So you know you're going to have to convert the grams to moles. So again, in case you're wondering, like, well, wait, what? Let's do this problem again, but this time I'm going to actually take this one down here, okay? So that I can do it on another page, okay? So you all can see the difference here. All right, so here it is again. All right, so again, don't worry about what was in the previous problems. So don't even look at letter A, okay? We're not concerned about letter A. And don't even look at letter B, okay? We're not concerned about that information. What we are concerned about is, of course, letter C. So again, what you got to start back over with what they gave you in the initial part of the problem. You were given 1.5 moles of neon gas, and you were also given 8.00 liters. Okay, so before I go any further, let me write that down again, okay? So your V1 was equal to 8.00 liters, and my N1, okay, was equal to 1.5 moles. You're looking for your V2. That's what they asked you previously. They want to know the final volume. It says it right here. What is the new volume? Okay, so to find my N2, they gave me what? It says a sample of 25 grams of neon is added to the 1.5 moles of neon gas in the container. So you know what you're going to have to do? You're going to take the 1.5 moles plus the 25.0 grams of neon. But guess what you're going to have to do? You've got to convert the 25 grams of neon to a mole. Okay, so this is where what you learned several chapters ago, maybe 2 months ago, with converting grams to moles. So for this one, I've got to convert 25 grams of neon to a mole in order to do this particular part of the problem. Okay, so 25 grams of neon times. Now, on the very top, I'm going to put 1 mole of neon. And on the bottom, I'm going to look at my periodic table and know that the weight, the molecular weight for neon is 20.18 grams. Okay? So again, we're going to cross out our grams of neon, but we're going to divide those two numbers. Okay? So we're going to say 25 divided by 20.18, and that gives us 1.23. And since we only need 2 of those significant digits, we're going to say 1.2. So that's 1.2 moles of neon. So what you're going to have to do, remember, you can't forget, excuse me, you're going to have to add, okay? Let me highlight this for you. You're going to have to add the 1.2 moles of neon plus the 1.5 moles of neon. Because remember, they said they added 25.0 grams of neon to the 1.5 moles that was initially in there. So you're going to have to add those two numbers together that I highlighted in pink to get the total new moles, okay? To get your total N2 or your total final mole count. So that's going to be equal to 2.7 moles, okay? So we had to do several things in order to establish our answer. So now, again, we're looking for V2. So let me put this in a different color so you all can see that. Okay, remember, V2 is equal to, go back up here to your previous formula, V1 times N2 divided by N1. V1 times N2 divided by N1. Okay? Thank you, LOL. Okay, so now what I need you all to do is to plug in these numbers. So remember, if our moles increased, guess what else is going to happen? Our volume is going to increase. And let me tell you this much. If it was initially 1.5 and then it goes up to 2.7, let's just round it off to 3. I can tell you right now that our moles doubled. And because our moles doubled, guess what your volume is going to do? It's going to also double, okay? So your V2 is going to equal to your V1. So let's go back and look at that value so we can have that here. So that's going to equal to 8.00 liters times 2.7 moles divided by 1.5 moles. Again, you're going to cross out your moles because you don't need those anymore because you're looking for V2. So V2 equals, let's plug this into our calculator. We've got 8.00 times 2.7 divided by 1.5, and we get 14.4 liters, okay? So it was almost double what we initially started off with, okay? 14.4 liters, and that is your answer right there. Okay? Now, are there any questions regarding this particular problem that we just did right here? 14.5. Okay. So now, do y'all want to do one more of those, or do you want me to do the last topic on molar volume, because this is a little different? Okay. Last topic. All right, got you. Someone said one more example. Okay, let's do one more example then. Okay. We will do, yes, so 2 people said one more example. I got y'all. Okay, so we're gonna do 14.6. I'm sorry, 11.46. 11.46. All right. We'll just we'll do letter A. Okay, we'll do letter A. No, better yet, let's do letter B, because this one is dealing with a new volume, a new mole problem. Okay, so we'll do that one. Let me put the formula back up here again so that you guys will know what we're working with. Again, V1 times N2 equals V2 times N1. That's the base formula, but we can remix this formula to ensure we get our answer, okay? So let me go ahead and highlight things that we have in the problem. Again, we're doing letter B, okay? We're going to do letter B. All right. Initially, in this top part, it says, a sample containing 4.80 grams of oxygen has a volume of 15.0 liters. Remember, pressure and temperature remain constant. Letter B says oxygen is released until the volume is 10.0 liters. How many moles of oxygen are removed? Okay, so that was a lot said in the problem, but we're going to break it down, okay? Break it on down. What did they give us in this problem? V1 was 15.0 liters. V2, according to V2, was 10.0 liters. So already we know that our volume has dropped. It has dropped. Since our volume has dropped, guess what we need to do next? We need to look at our moles. So in one, they gave us 4.80 grams of oxygen. And for N2, they want to know how many moles of oxygen are removed. Okay? So that's what you're looking for. You're looking for N2. In other words, since they removed it, that means they dropped. The amount will drop. What you have to keep in mind is that since this is all about moles, you've got to do what? You've got to convert these grams here to a mole. So you have to look at your periodic table and find the molar mass, okay, of oxygen. Since I have two of those times 16.00, that's equal to 32.00 grams per mole, okay? So now what you're going to have to do in this problem is convert the 4.80 grams of oxygen times, on the top, you're going to put 1 mole of oxygen, and on the very bottom, 32.00 grams of oxygen. You're going to cancel out your grams of oxygen, okay? Cancel those out, and go ahead and do your operation here, okay? Okay, Kiwi. Okay. All right. So now you've got 4.80 divided by 32.00, and we get 0.15 moles of oxygen. Okay, that's what you get. That's the moles, but you know what you have to do, okay? Just so you don't get confused, okay? Just so you don't get confused in the problem. Right here, where you see 4.80 grams, you're going to replace that number with these moles here. That's your N1, okay? The 0.15 moles. That's your N1. So now let's plug these values into our formula, okay? So again, we're looking for N2. So the formula for N2, if I go back to the base formula, the formula for N2 is going to be V2 times N1 divided by V1. V2 times N1 over V1. So let's go ahead and write that down. V2 times N1 over V1. And let's plug in our numbers. Again, we already know that the value that we get is going to be less than 0.15. So V2 was 10.0 liters. N1, which is what we just calculated right here in this yellow, 0.15 moles divided by V1, which was 15.0 liters. Let's cancel out our liters because that's not what we're looking for. And we're left with moles. So now, hey, Yasmin, how you doing? You're going to say 10 times 0.15 divided by 15. And we get 0.10, okay, moles. And guess what? The answer that we just solved for is less than the number that we initially started off with. So it did drop. So 0.15 dropped to 0.10. Okay. That's it, guys. Like that's how you do these problems. Okay. They're not difficult at all. And I'll say this, as long as you know the formula that you have to use, and as long as you remember certain things you're going to have to do in order to proceed with the problem. Like in this case, if you use that grams in your number, you would get the wrong answer because what you're going to be looking for is not going to match up had you kept this number as 4.8 grams. Okay? You're welcome, guys. You all are so welcome. So now let's go ahead and get to that last problem, okay? And the last example here is talking about calculating molar volume to find volume at STP, okay? So this is the last one that I'm going to do really quickly before I have to get past my day here, okay? And whenever you're talking about STP, there are things that you need to know. Anytime, and this is on a lot of your AP chemistry exams. This is on the MCAT, okay? Jose, yep, you are correct. You got to deal with that 22.4. You are absolutely correct, okay? So let me see if I can pin your comment, okay, for what you just stated. So STP means that at standard temperature and pressure, your temperature, of course, if you're using it, it's going to be 273 Kelvin, and your pressure, okay, would be 760 millimeters of mercury, or it could be 1 atm. And your temperature could also be in 0 degrees Celsius, depending on what they start you guys off with, okay? Now, for your volume, your molar volume, okay, whenever they're asking about volume, your molar volume that you're going to use also is what Jose said, the 22.4, okay, liters. So those are some things that you need in order to solve this problem, okay? Those are some of the things that you will need in order to solve this problem. Now, in this particular case, though, okay, notice that they gave you 64 grams, but they're asking for the volume. What you're going to have to do is take the 64 grams, and you're going to have to convert that to a mole, okay? So the 64 grams of oxygen, we've got to convert that to a mole of oxygen by using the number that we had in the previous problem in terms of the molar mass, okay? So the 64 grams of oxygen, and on the top, we're going to say 1 mole of oxygen, and on the very bottom, what are we going to put? The 32. That's the molar mass of oxygen, okay? So you're going to cancel out your grams because you don't need your grams. And then you're going to get this value here in moles. So you're going to divide the 64, okay, right there, divided by 32, and you get 2. So this is 2 moles, 2.00 moles of oxygen. But we're not done, okay? We're not done. Because in order to do this problem, you've got to now multiply that times the 22.4 liters. So here's what you need to know. 22.4 liters, okay, is equal to 1 mole of whatever your gas is, okay? Whatever your unknown gas is. So that was the one part I left off. So for your molar volume is 22.4 liters of whatever the gas is, okay, per 1 mole of gas. So for the step here, for this final step, you're going to say the 2.00 moles of oxygen times, since you're looking for liters, 22.4 liters divided by 1 mole, okay, of that oxygen. And then you just multiply those and you get your answer accordingly. So your answer is 44.8 liters of oxygen, okay? 44.8 liters of oxygen, okay? At STP, if you want to be more specific, at STP.